Alright, welcome back to the Unit 5 full review guide. Right, this is my series on Unit Review Guide, breaking down the content assessed on the AP Calculus APA exam. Before we begin, if you want to find the full notes for all of these review guides, just check my bio. I have a link to my website with all my resources. So definitely go check that out. Without further ado, let's just begin. Topic 1.5.1, Using the Mean Value Theorem. Now, you just need to know the statement, right? If f of x is continuous over the interval closed, a comma b, and differentiable over a comma b, the open interval, then there is a c in the open interval a comma b, such that the derivative of f at c is the average rate of change. So we can break that down really quickly. We need to check that f is continuous on the closed interval and differentiable on the open interval. Oftentimes on FRQs, we might need to write, because it's not given, that we might need to write f is continuous because it is already differentiable, right? If you remember, differentiability implies continuity. And the theorem, if those two conditions are met, then there is some place where the instantaneous rate of change is the average rate of change. So topic 5.2 discusses the EVT and global versus local extremum and critical points. The extreme value theorem simply says that if f is continuous on the closed interval a comma b, then f attains at least one maximum and one minimum value on that interval. Now, let's define a critical point. A critical point of a function f is, basically any point where either the derivative is undefined or zero. So these are very important for candidates because we have this theorem that states that if a point is a local extremum of a function, then it is also a critical point. That means if we can find points where the derivative is zero or undefined, we can test them somehow to see if they are local extremum. Topic 5.3, determining intervals on whether a function is increasing or decreasing. So here I wrote the definition of increasing and decreasing. Basically, as x increases, f increases if f is increasing. But if it's decreasing, then as x gets larger, f gets smaller, right? That's the definition. And with the derivatives, right, with the calculus interpretation, if for every point in an interval the derivative is positive or negative, f is increasing or decreasing respectively, right? So that's very useful. And normally at a point we'll say it's increasing or decreasing if the derivative is positive or negative, although technically that's not true. You can think of it like that. So the sign of the derivative tells us the monotonicity. Topic 5.4, using the first derivative test to determine local extremum. To define local extremum, right, as this theorem told us, we just need to find critical points of f first. Alright, using the first derivative test, now we need to find intervals of increasing or decreasing, right, which we can use the sign of the derivative between the critical numbers. But how do we do that? Do we need like complicated algebra? Well, we can use test values. Since we've already found where a function is equal to zero, right? As long as it's continuous, we could take one test value in the interval, and if it's positive, the whole interval is positive, and if it's negative, the whole interval is negative. So the first derivative test is a theorem. It tells us that if a point is a critical point of f, then if f prime changes sign from positive to negative, it's a local max, and if it changes sign from negative to positive, it's a local minimum, right? Also note that a local minimum or local maximum is a relative minimax. So for example, find a local extremum of f of x if f is equal to x cubed over x plus 1. Our first step is always to find f prime, alright, and hopefully you know how to take the derivative. So when you do that, you'll notice we have this, and then we can simplify. And here we do want to actually use some algebra, simplify it out, and we set that to be equal to 0. Why? Well, either 0 or undefined, right? So we need to be careful there. Additionally, I wanted to leave this here so that you would note it's not just when it's 0, we also need to be x is equal to -1. Why? Because that makes the denominator 0, right? But what's the catch, right? You may be thinking, what's the catch? Well, this is kind of a critical point. We do want to test it, but it's not included in the domain, right? So you'll see this often. So I'm writing it here so that you guys know, but and it can change monotonicity, but it's not a local min or local max, but it is a point you need to include in your sign chart. And what is a sign chart, right? Well, we have these critical numbers, right? And that's what we found up here, where the derivative is 0 or undefined. We take these intervals, right? And however you may have learned, we just take the intervals, we take test values between, each interval, negative infinity to the critical number and in between critical numbers. And we say the sign, all right? That sign corresponds either to a down arrow for decreasing or an up arrow for increasing. And now we just check when a down arrow becomes an up arrow or an up arrow becomes a down arrow. We see right here, this down arrow becomes an up arrow. So at -3/2, the function is, it looks like it's decreasing, it's increasing. That's a local minimum. So we can say f has a local minimum because f prime changes sign from negative to positive there by the first derivative test. Topic 5.5 allows us to determine absolute extrema. You need to know this. It shows up a lot on the AP exam, especially on FRQs. Now, in order to find absolute extrema, we just need to check critical points or endpoints, right? So, if we're asked to find the global extrema, right, or the absolute extreme on this interval, we just need to check for critical points as we did before. So we're going to take the derivative and solve for when it's 0. It's defined everywhere, so it's 0 when x is 4/3 or -2. We don't need to check -2 because it's not included in our interval. And we test 4/3 because it's a critical point, and -1 and 4. Justify why those are your candidates. Say that you're finding f of x at those points because these two are the bounds, right? The endpoints, and this one's a critical number of f. Write that, okay? Now we have f of -1. We plug that in, we get that's 8. F of 4/3 is this thing, but and then f of 4 is 48. So what do we get? We have f has an absolute max of 48 at x equals 4. If you write that, you cannot lose points. Just write it has an absolute maximum value of whatever at the point. F has an absolute minimum value of whatever at the point. Topic 5.6 discusses concavity. Now, concavity has a lot of interpretations, but I won't discuss that for now. I'll just stick to the derivative, right? So we say f is concave up if the derivative is increasing, and it's concave down if the derivative is decreasing. That should kind of make sense, pretty easy to memorize. And also the second derivative, the sign, tells us concavity. If it's negative, then it's concave down, and if it's positive, it's concave up. An inflection point, which you need to know, is a change in concavity, right? Basically, the sign of f prime changes, or sorry, f double prime, or you have a change in monotonicity of f prime, meaning it changes from increasing to decreasing or decreasing to increasing. So now we're going to learn how to use the second derivative test to determine extrema. If you are not familiar with this, right, I'll just show you the method. If you are not familiar, review my video. It'll really help you. Just look at my channel on second derivative test. This is the theorem, right? If we have a critical point, this is all it's saying. If we have a critical point and the second derivative is positive, then it's a local minimum. And if the second derivative is negative at the critical point, it's a local max. How to remember it? If f double prime is positive, it's concave up, so it's gonna have a local minimum, right? Assuming the derivative is 0. That's pretty easy to memorize. And if it's concave down, right, the second derivative is negative and the derivative is 0, it's a local max. Now, I added this note. If both first and second derivative are 0, we have to use the first derivative test. So yes, this can replace the first derivative test, but there are times where we do need to go back and use it. The College Board also wants you to know this, and that is when a continuous function has only one critical point on an interval on its domain, and that is a local max or local min, then that is the absolute max or absolute minimum on that interval. Now, you don't, obviously it's not like you're going to memorize it, but sometimes on FRQs for justification for absolute min or max, if you have only one critical number, if you can justify why to the left it's decreasing and to the right it's increasing, or sorry, to the right it's decreasing and to the left if it's increasing, or the other way around if it's a local min, then of course you can justify that that has to be the absolute max or absolute min. So keep that in mind. Alternatively, you can go back up here and just use the candidates test. Topic 5.8, all right? Although you're not going to be assessed on sketching graphs anymore, although they used to ask that, you should know some critical features of the first and second derivative and what that tells us. Here I outlined it, all right? If f prime is positive, f is increasing, right? So interpret that graphically. When f prime goes from above the x-axis to below, it's a local max, right? And if it goes from below to above, it's a local min. If f prime, right, is 0, anywhere where it's 0 or undefined, right, it is a critical number. All these local max and local min are also critical numbers. Also, if it's undefined, like it's a little gap here, right, a whole critical number. Inflection points are just when f prime has a local min or local max, when it changes monotonicity, right? So if we have a little cup here like this, and this is f prime, this is an inflection point. For f double prime, an inflection point is simply when it's 0, and most importantly, not only is it 0, but it changes sign. F double prime changes sign. So here I wrote some notes. If you want, you need to know that. That could be asked. Now, skipping ahead, you may notice it jumps some topics. That's because it's all optimization problems. So, what is optimization? We're trying to take a real life problem and we're going to use calculus to maximize or minimize something. Maybe economics, maybe this problem. So, how do we solve it? Similar to related rates, first we're going to create a function and variables. In order to do that, we need to name everything, right? Then we want to find what functions or what equations, sorry, relate the variables. Then we want to find the function that we're asked to maximize. Maybe that be, we want to, or minimize time, distance, whatever. And we want to use calculus that we've just learned to minimize or maximize the function. So let me break down this problem quickly. We have a rectangular swimming pool, 100 by 20, and we start over here. This is us. And we want to get to the opposite side where a trophy is. We swim at 10 feet per second, but we run around the pool at 20 feet per second. What's the fastest time we can get to the trophy? This is an optimization problem, and we're going to assign variables. So first, we're going to travel x units, right? Some x units along here until finally we're going to jump in and swim. Maybe we don't end up jumping in and swim and we just come around along here. We should test that, right? If we don't swim at all and we just run along. But typically that won't be the fastest way. We're going to have to run some and then jump in and swim across. Also, swimming across directly, although it is the shortest distance, not the smallest time. I want to minimize the time. So we're going to let x just be this distance that we travel before we jump in and swim. And let capital T be the time it takes. We can calculate it by first using x and using the fact that we run at 20 feet per second, right? So that gives us x over 20 time, right, seconds to travel this distance. Then this distance in terms of x, right, this is 100 minus x, this is 20. So using Pythagorean theorem, we can get this distance in terms of x. And of course, since we're traveling 10 feet per second, we divide by 10 and we add those two times to get the total time, right, which varies with x. We take the derivative and we solve for when it's 0 and we get the following. Normally, if we're on an MCQ, we know this is probably the time, right? Or sorry, the x, not the time, but the x, and we're done. We put that in, we solve. But in fact, if we plug that in, we get 6.42 seconds approximately. If you also check for when x is 100 or when x is 0, right? Since you can think of that as your interval, right? Those are the extreme cases. You swim directly or you do this. If you check both of those cases, you'll notice that those are both more time than 6.42 seconds. So you can safely conclude that the fastest you can reach the trophy is in 6.42 seconds. This may be asked using height or some other thing. You just need to know how to apply optimization. And finally, we end off with exploring behaviors of implicit relations. College Board does ask this. I've seen it. Basically, we're going to consider a curve f of x comma y equals 0 or equals some constant or just an implicit defined curve. Now we look at the derivative. If the derivative is 0 or undefined, we have a critical point. Critical point, what does that mean? That could be like a local max or a local min, but in the context of the implicit function. So if we have, I don't know, an implicit function like this, maybe this is your local max and this is your local min. Also, if the second derivative is positive, then it's concave up, and if it's negative, it's concave down. If the first derivative is positive, it's increasing, and if the second derivative is positive, it's decreasing. Remember, it's at points. This is all basically emphasizing that even for implicit relations, they follow the same rules as standard derivatives. Also, what I've seen that I didn't necessarily add, but what I have seen is that vertical tangents for implicit differentiation, right? For implicit functions, vertical tangents are just when the numerator is not 0 and the denominator is 0. And whenever it's a horizontal tangent, then the denominator is not 0, but the numerator is 0. Pretty simple. Same thing like a normal function, right? A normal derivative. So let's get a quick practice problem in, very quick. Consider this implicitly defined function as a curve. At the point 0, 1, is it a local max, a min, or neither? Using implicit differentiation, which you should be familiar with, we get y prime, which is dy dx, is 2x over 3y squared minus 1. Now, you should know how to take a second derivative implicitly. We're going to take this derivative here, right, and we're going to get some terms as just normal and some terms with y prime, but we already have y prime. So we're going to do some algebra. You'll notice we plug in our value for y prime, and we get what this is, right? Doing some algebra, we get y prime of 0, 1. So first we plug that in. That's 0, so that's our candidate. Remember, that's our candidate for local extremum. We don't have anywhere where it's undefined except for when 3y is equal to 1 or y squared is equal to 1/3, but we're not considering that because that doesn't work. You can check that. But when it is 0, right? Sorry, so he gave us a point, right? So we're checking specifically at that point. It is 0, right? And the second derivative, right? What is that? Well, we plugged it in. It's positive. So we go back to, our heads. Normally, if we have this first derivative, right, is 0, right? So it's a horizontal tangent. And the second derivative is positive. That's a local minimum. So that's our answer. Essentially, what you need to take away is that an implicit relation behaves very similar to explicit functions. That's it for Unit 5. If you want to get these notes, remember, look at my bio, get the link, get the file. It's completely free and has a bunch of other resources as well. And be sure to join me for Unit 6. Keep studying, keep reviewing, and good luck on that AP exam in May.